So for this question, we have graphs. So let's do our Oizerga due diligence. Origins, all 0, 0. Good. Y-axis, kinetic, 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 kinetic. So they're all kinetic energy. The x-axis, work, 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 work. They're all work. The intercepts are varied because it's a multiple choice. And what we can read off the graph is kinetic energy and work. The slope is the change in kinetic energy over the change in work, which they have units of joules over joules. So it's just a ratio of those two, a ratio. Now, immediately when we're seeing change in kinetic energy and change in work, we should be thinking about the work energy theorem. In fact, the work kinetic energy theorem. That's what our mind should be connected to at that point. And the area would be the kinetic energy times the work, which would have units of joules squared. And what square energy is, I don't really know, but that's what it would tell us. So then we're told a constant force acts on a mass. Okay, so it's initially at rest. So V0 equals 0. Well, we know the work is the average force times the distance, and we're told that this is constant. And it's initially at rest. This sounds an awful lot, again, like the work kinetic energy theorem going on here, which the following shows the relationship between the kinetic energy of the mass with the work done on the mass. Well, the work done on the mass goes into changing its kinetic energy. And they are equal to each other according to the work kinetic energy theorem. So let's see here. The first one says when there's 0 work done, there's 0 kinetic energy. And as we do work, that work goes into the kinetic energy. That work goes into the kinetic energy. Whatever we put into whatever work we do goes into the kinetic energy. That looks like it's our answer, but we're not done. What choice B says is that the work has no effect on the kinetic energy. There's no friction. We have a constant force over a distance, and there's no friction. The thing must accelerate. F net equals ma, and the only force acting on it is that average force, so it must accelerate. This can't possibly be true because V must increase, and therefore the kinetic energy must increase. If we look at choice C shows us starting at 0, and as we do work, it goes into the kinetic energy. But what we can see is depending on, even if we put in equal increments of work, don't produce equal amounts of change in kinetic energy. So although doing more work brings about more kinetic energy, the fact that the rate isn't constant is problematic. And so we would see that choice A is a better choice than choice C. And choice D says that as we do more work, the kinetic energy goes down. Now, the case where this might happen is if we had some object that was moving, say it's got a velocity in that direction, and then we apply a force in the other direction. The force in the other direction would cause it to slow down, which would reduce its kinetic energy. But that's not what this situation is. The situation says that it's initially at rest, and if the kinetic energy is 1/2 mv squared, if the velocity is 0, the kinetic energy should be 0. And if so, the first amount of work we would do is a small amount of work. And a small amount of work, it says here, is bringing about a huge change in kinetic energy. And somehow doing that work would reduce it. The other thing to keep in mind is that if the particle starts at 0, it doesn't matter if I apply a force in this direction, it will accelerate to the left. And if it's at rest and I apply a force in that direction, it will accelerate to the right. So D just does not make any sense at all because it requires the thing to already be moving. So we not only shown YA as the answer, we've ruled out why the others are not correct.